Oh, hello and welcome to lesson 3.4 day 1, velocity and other rates of change. This includes applications of the derivative. In class, remind me that we need to do these notes for the homework so that you know how to get the problems 1 to 4. There are lots of words on this video. Please stop the video at any time and write them all down. The instantaneous rate of change, we know this definition right here for derivative. So that is the definition we are always going to remember. We can use our other tricks to take the derivative, but remember that the derivative is always a limit as you get closer and closer to a point, provided that it exists. All right, we're going to start out by writing the volume of a sphere with respect to r. And the volume of a sphere is 4/3 pi r cubed. Okay, that's our first thing they ask us to do. The second thing is write the instantaneous rate of change of the volume with respect to r, the radius. So what we do is take the derivative of this volume with respect to r, and we are going to use our power rule with respect to r. 4/3 and pi are constants. So the derivative of r is 3r squared. We multiply all of that together, and we get 4 pi r squared. All right, so that is part 2. These 3's cancel out. All right, now we're going to evaluate the rate of change using what we just found out, that the rate of change of volume with respect to r is 4 pi r squared. And we are going to plug in those two values so that we see the different rates of change. At r equals 2, we have the change in volume equals 4 pi times 2 squared, which is 4, or 16 pi. And also, when r is 5, our rate of change is 4 pi times 5 squared. And that equals 100 pi's. So you can see that as r gets bigger, the rate of change of the volume of the sphere also gets much larger. All right, what if r is measured in inches, volume is measured in cubic inches? What is the measurement of dV, dr? And what they're looking at is actually what are the units. So volume is inches cubed, and r is inches. So we end up with inches squared as our unit. Okay? Next, we're going to do, and we have lots of problems like this, and they're always on the ACT, on the AP test. And I've highlighted the words that are important because you're asked the position, sometimes you're asked the acceleration, sometimes you're asked the displacement, and you've got to know the difference between those words. This is basically a page of all the definitions that we use: position, instantaneous velocity, acceleration, etc. All right, so position, and this is our given position function that we're going to use to demonstrate all of this. So our position is actually this function. This is our position function right here. So position is just whatever your function is. Okay, that's our first word. Whatever your major function is. Instantaneous velocity is the derivative of that function. So the derivative of s, ds dt, equals 6t plus 5. And that equals our instantaneous velocity. And that's not to be confused with our average velocity, which we'll do down here. Our acceleration. Acceleration is the derivative of the velocity function. So we take the derivative of our velocity. It's also the second derivative of our position, but that would just be equal to 6. So acceleration is a constant. Just so that you know, acceleration in this function is a constant. Next, we have displacement. That means a change in position from the beginning to the end. So let's say we start at time t equals 0 and we go to time t equals 3. All we're going to do for displacement is take the change in the general function, the change in s. So we have s at 3 minus s at 0. And we plug in those two numbers to get our answer, and that gives us the change in s, which we call the displacement. Okay, so whatever that number is, I think it's 38 minus -4, so we get 42. And that would be in inches, feet, meters, whatever your unit is. Okay, so let's move down our speed and our average velocity a little bit. Average velocity is the displacement over the time. So it's also the change in s over the change in time. Okay, so that's our average velocity. We found this before when we've done things. So the average equals the function, and I'll call it s because that's what it is. S at 3 minus s at 0. We're going to find the average velocity between t equals 3 and t equals 0. And 3 minus 0. The difference in time, the difference in s over the difference in time. All right, so if you calculate all that out, we already did the top, that was 42. We divide by 3, so whatever that number is, 14. 14, and it's in units, so distance over time, whether it's feet per second or meters per hour, a distance over time. All right, now the speed is fairly easy because it is going to be the absolute value of the velocity. So whatever you get for the velocity, the speed is going to be the absolute value of that. In this case, the average speed would be 14. And if we calculated at t equals 3, the velocity function we said, or dv dt, is equal to, ds dt is 6t plus 5. So if we calculated that for 3, we'd get 18 plus 5, or 23. All right, and just so you know, these are your free fall constants. Often they're negative. You don't really have to memorize those, but you will see them sometimes in the book or in problems. Okay, so now we have a particle motion problem. All right, so particle motion is what we do a lot of in calculus. So, and what we use the derivative for, to see how the particle is moving along a line. So this particle is moving along a line with this position function. And what the first question is find the displacement during the first 3 seconds. The displacement is the change in s. So we have s at 3 minus s at 0. That is displacement, where that particle is going in that time frame. So if we plug a 3 into this equation, we get -7. And we subtract, if we plug a 0 in, we get 2. And therefore, our particle has a displacement of -9. It's okay to have a displacement of negative number. That means it's moving backwards or to the left. The next problem is find the average velocity. The average velocity is, and then it says during the first 5 seconds. So we're going to take the distance at 5, or the position at 5 minus the position at 0 over 5 minus 0. That gives us our average velocity. So we already found that the numerator is negative 9 over 5. So this time we have negative 9 fifths. Did I do that wrong? Oh, I'm sorry. We're doing 5 now, not 3. So the particle at 5 is negative 3, and the particle at 0 is 2, and then we divide that by 5. So we have a negative 1. So the average velocity of the particle during the first 5 seconds, and this would be meters per second, this would be meters, just so that you know what the units are. And I know that because that's what it told me, meters and seconds. Now the instantaneous velocity is going to be the derivative of our function. So the instantaneous velocity is 2t minus 6. And when the particle is, when t is 6, time is 6, we get the velocity at 6 equals 12 minus 6, or 6 meters per second. All right, the acceleration is the derivative of the velocity. So I'm going to take the velocity of this function, which is just 2. So 2 meters per second squared is your acceleration. All right, the last question asks us to describe the motion of this particle. So what we're going to do is take our velocity function and bring it down here and work with that. All right, so the first thing we're going to do is the particle is either moving forward, backwards, or you could say left and right, forward and backwards, or it's stopped. So let's find out where it's stopped, where the velocity is 0. Okay, so for this function, the velocity is 0 at t equals 6 over 2, or at t equals 3, right? If we solve that equation, so the particle is stopped at t equals 3. So what we need to know is where, what is it doing between, does it change direction? Describe the motion of the particle. We're gonna start at 0, because this starts at 0. So from 0 to t to 3, we want to know is the velocity positive or negative? And then at t equals 3, we know it's stopped. And at t greater than 3, we want to ask the same question. Is the velocity positive or negative? So if we plug a 1 into 2t minus 6, a number between 0 and 3, if we plug a 1 in here, this is a negative number. Therefore, the particle is moving backwards or left, whichever way you want to. Because the velocity is negative, it's moving backwards or left. Now, if we plug a number greater than 3 into the velocity function, we get a positive. Therefore, the particle is moving forward or right. So, to summarize, this particle at 0 to 3 is going backwards, then it stops, and then it goes forward for the rest of the time. This is a velocity graph, or a derivative graph. And what we want to do is see how the student who's walking in front of a motion detector, and it's recorded every second for 30 seconds, and we want to see how the student is moving. So, when is the student moving forward and backwards? Now remember, this is velocity. Anytime the velocity graph is above the line, she's moving forward. Anytime you see it above the line. Anytime this graph is below the line, she's moving backward. And when the function is equal to 0 on the x-axis, that means she stopped. Okay, so always think of these derivative graphs like that above the line, positive velocity, below the line, negative velocity. All right, when is she moving forward and backward? All right, so she's moving forward from, and I'm going to write this in intervals, I think. So from 0 to 6, she's moving forward, right? She's also moving forward from 18 to 30. Those are all the times that that graph is above the line. She is moving backward just from 9 to 18. 9, comma 18. This is writing in interval notation. When is she standing still? She's standing still from 6 to 9. When is her speed a maximum? And graph the speed. Now remember, speed is an absolute value function. So that means that this is -4. So I need to put a +4 up here. Because when I graph the speed of this, it's the same as the velocity graph, except anytime speed is negative, I am going to make it an absolute value. So her speed is a maximum, right, between 12 and 15. Between 12 and 15, her speed is a maximum. All right, so when is her acceleration positive and negative? All right, this is probably the most fun one. Okay, so her acceleration positive or negative. I've changed the screen a little bit. Remember that her acceleration, part D, her acceleration is the slope of the velocity graph. We know the graph up there. So anytime that acceleration is positive is when our slope is positive. All right, so where is our slope positive on this graph? Well, it's positive between 0 and 3. Between 9 and 12, it's negative. Between 15 and 21, it's positive. 21. Between 15 and 21, and anywhere else, it's positive. 0, negative, 0. We're looking at the slope of this the slope of this graph. Now, acceleration is negative wherever the slope is negative. So between 3 and 6, these two numbers should not overlap either. Between 9 and 12, a graph cannot be positive and negative. And then between 24 and 27. And note, anytime that you have a flat line, that means your acceleration is 0. So A equals 0 at wherever the slope is 0, 6 to 9, 12 to 15, 21 to 24, and 27 to 30, all of those intervals. The slope is equal to 0. All right, last page. These are two problems on your assignment. I think 44 and 45. You have a position position function, and the first question is, when is this particle moving to the left? Now we know that a particle is moving to the left whenever the velocity equals a negative. Okay, so we want to find out where that velocity is negative. When is the particle at rest? Whenever the velocity equals 0. All right, so those are our two scenarios we're looking for. First thing we need to do is take the derivative. So derivative of 2 is 0, 7t is 7, and minus 2t. That is our velocity function. Let's set this equal to 0 to answer number 45. T is equal to 7 halves. You subtract 7 from both sides and then divide by a negative 2. So we need to look at both sides of this. This is the answer to number 45. Where is it 0? When is the particle moving to the left? Okay, so let's try a number between, our two choices are 0 to 7 halves or 7 halves to infinity. Since we think we're starting at 0, time greater than 0. This is how I know that. Okay, so we could try a number bigger than 7 halves and see, and remember you're looking at the velocity function, so 7 minus 2t. If we put a number in here, this is 3.5, what if we put a 4 in here? If we put a 4 in here, this equals a negative number. So right here is where the particle is moving to the left. So that is our answer. Anything bigger than 7 halves. I could also write this t greater than 7 over 2. All right, those are our two answers, and that is our lesson for today.